Good evening. Today we are going to talk about projectile motion, if you give me a minute. Share the screen. Now, a projectile is an object that moves only under the force of its own weight. The only acceleration is g, therefore the only force, all the acceleration is g going downward. That does not mean it's only moving downward, only that the acceleration is downward. There can be a horizontal component of velocity too. But that velocity, the horizontal component of velocity, must be constant. Now, here are the equations for projectile motion. Again, the acceleration in the x direction is 0. Therefore, the acceleration component, therefore the velocity component in the x direction, the horizontal direction, must be constant. And the x component itself, the displacement, is the integration. We take where the constant is the initial speed times the cosine of theta, where theta is a constant too. Of course, this angle changed, but we're treating theta, this theta we're using, it's the constant, it's the launch angle, the angle it starts. Then, as I said, x is the acceleration, is the integration of the x component of velocity with respect to time. We do this integration of v naught cosine theta. It's v naught cosine theta times t, plus the constant of integration, which is the initial displacement in the x direction. We can usually call this 0. Acceleration in the y direction. Again, the only force is weight. The only acceleration is gravity. A of y, it's negative g. It's negative because we're going downward. Down is negative, up is positive. For the velocity, we do take the integration. Integration of negative g with respect to t is negative g dt, which is negative gt by the power rule, plus the constant of integration, which is the y component of the initial velocity, which is the initial speed times the sine of the launch angle. Now, the y component itself, it's the acceleration, is the displacement, it's the integration of the velocity. By the power rule for integration, this is gt squared over 2. Again, by the power rule, we add t here, and again, another arbitrary constant of integration. This is the initial y displacement. It's the initial height. In a lot of textbooks, that's h. Let's do some problems. The baseball is thrown straight upward. What is the ball's acceleration at its highest point? The acceleration is constant. So the acceleration is always negative g in the y direction. Okay, it's negative g downward. Soccer ball, how about this one? At rest of the ground is kicked with an initial velocity of 10 meters per second and a launch angle of 30 degrees. Calculate the total flight time, assuming the air resistance is negligible. Now, it's going to go like this, okay? Up and down. It's going to end its flight time when it hits the ground. So we're not actually going to take x into account. We're going to take y into account. So we have y equals negative 1/2 gt squared plus v naught sine theta t plus y naught. And it's going to hit the ground. Y is 0. We're going to set this equal to 0 and solve for time. Now it starts on the ground too, so the initial height y naught is also 0. And now look what we can do here. We can factor out a t. No, this t, sorry. This t is not here anymore. It's factored out. Here we have two solutions. T is 0. This is not the answer because it corresponds to the starting point. Again, just like we said earlier, our initial height is 0, so it starts on the ground, and we just got that solution back. It's the other solution that matters. And so we're solving for t. And we get 2 over g v naught sine theta. So let's put the numbers in. I'm just going to call this 2. G is 9.81 meters per second squared. The units are consistent, so I'm not going to put the units in, just the numbers, because this velocity, 10 meters per second, is also in MKS units. Meters per second squared, meters per second, it comes out seconds. And the sine of 30 degrees, theta is 30 degrees, so the sine of theta is 1/2. These 2's go away, and to two significant figures, this is going to be 1.0 seconds. Number 3. A stone is thrown horizontally with an initial speed of 30 meters per second from a bridge. Find the stone's total speed when it enters the water 4 seconds later, assuming that air resistance is negligible. Now, I have total speed there, but that's just kind of a redundancy to say that. What we need is the speed. That's just to remind you that speed has an x and y component. The v of x is v naught cosine theta. If it's thrown horizontally, theta is 0. So the cosine of theta is 1. So this equals v naught. V naught sine theta, Vy V naught sine theta, minus gt. Again, theta is 0, sine theta is 0. This term goes away. We're left with negative 9.81 meters per second squared times 4 seconds. This goes away. We're left with 3 sig figs, 39.2. We're using 1 extra sig fig calculations, meters per second. Now, speed is a Pythagorean identity. Plug in the numbers. Now, if we look at this, 39.2 is about 40. 30 squared is 900. 40 squared is 1600. This is going to be about square root of 2500, which is 50. So I'm going to say this 2 sig figs, this is going to be around 49 meters per second. Now, let's move on. And let's do some exam problems. Now let's look at this. The paths of 3 projectiles are shown in figure 312. Which projectile spends the most time in the air? Now let's look at this. We have, notice, you remember the equations are quadratic for this projectile motion. It's linear in the x and linear in the horizontal, and it's quadratic in the y. So the whole thing is going to be quadratic. Substitute a linear for a quadratic, you get a quadratic. This is a symmetry. These all have a symmetry. It's going to take as much time to go to the top as it does to go to the bottom. These angles are going to be the same. This angle is going to be 60 degrees like this one, 45 degrees here, and 30 degrees. Now let's look at this. The peak here is the same for all of them. What does that mean? That means they're going to have the same critical point. At the peak, the velocity in the y direction is going to be 0. So let's look at this. We have y is negative 1/2 gt squared plus v naught y. That's your component of t plus y naught. This is your v naught sine theta. V naught y is your v naught sine theta. Now, since we're starting on the ground, this y naught is 0. V of y is when we take the derivative here, and we see the familiar formula. I'm just calling it v naught y and not writing in terms of the launch angle to see that this only depends, to show you how this only depends on v naught y. And solving for t at the critical point equals 0. T at the critical point is t is v naught y over g. And again, since this is symmetric, the time to come back is going to be twice that. But did these get to the critical point the same? Now the question is, did these all get to the critical point at the same time? If we plug v naught y over g in for t, right here and here, okay, we'll get the critical point itself, which is negative 1/2 g v naught y squared over g squared, so that's going to be negative 1/2. This is v naught y squared over g squared. The g's cancel out here. We're left with v naught y squared over g. And we put this in for t. This is also plus v naught y squared over g. And this is just going to be y. Notice that this is half of this and subtracted. It's just y critical, y max is squared over 2g. Now, notice then since all these y max points are the same, the y component of velocity must be the same for all of these, A, B, and C. And because of that, the time to land must be the same for all of them. So the answer is they're all going to hit the ground at the same time. The only thing that makes this different is the x component of velocity. In fact, if you launched something straight up with the same y component of velocity but 0 x component, it would hit the ground at the same time sans air resistance. Okay, assuming you could ignore air resistance. That is, assuming you can model as a projectile. An object is thrown horizontally with an initial speed of 10 meters per second. It hits the ground 4 seconds later. How far did it drop in 4 seconds? How far did it drop? Now, again, they're asked how far it dropped, not what the range is, not how far it went outside, not went outside, it went horizontally. Do we care about this for this problem? No, we don't. We only care about the y. Now, since it's thrown horizontally, what is v naught y? It's 0. The angle is 0, so if you write v naught y as v naught sine theta is 0. This term goes away. Now, we know that t is 4 seconds. And we know that y is 0 since it hits the ground. All we don't know here is y naught. So we have 0 equals negative 1/2 g, or I'll just put the numbers in. 9.81, the units are consistent. 4 squared plus y naught. And this is going to be 4 squared is 16. 16 divided by 2 is 8. 8 times 9.81 is going to be around 78 meters per second. 78 meters. Sorry, y naught is 78 meters. It's about 78 meters to 2 sig figs. And let's do one more. Two particles are simultaneously launched off the top of a cliff with the same initial speeds and angles as indicated in figure 3.14. What is the speed of the top projectile with respect to the bottom projectile as a function of time? Now look at this. They have the same initial speeds in equal and opposite launch angles. In the x component, they're going to be in tandem. Okay? They're going to be exactly the same. There's going to be no difference. In the y component, they're going to be equal and opposite. So Vy is going to be, or at least the initial velocity is negative gt plus Vy top and V wide bottom, B for bottom, now if we take the difference of these things, minus GT here, minus minus GT, that cancels out, 0. Negative negative here, V naught sine theta, negative negative, this is going to be 2 V naught sine theta. That is going to be the difference in velocities between these two if they are no longer models of projectile. That was an introduction. Thank you very much. That was an introduction to projectile motion. I hope you found that informative. And thank you and have a nice day.